Hello, this is Dr. Joe Trout from the physics program at Stockton University. And today we're going to talk about Chapter 9, ARIMA models, and this is part 1 of Chapter 9. So we're going to talk about stationarity and differencing and backshift notation, autoregressive modeling, moving average models, and non-seasonal ARIMA models, and go on to ARIMA models and forecasting. But first, let's take a quick review of Chapter 8. In Chapter 8, we talked about exponential smoothing. So if you think about the naive method, what we said was that any future value will equal the last value of the observation. And we also have the averaged model, where we took the average of all the observations and used that to predict the future. So now what we want to do is some method between those two. So we're going to take the weighted average between the most recent observation, and as the observations go further back in time, we will count them less. An extension of this simple exponential smoothing is the Holt's linear trend method. And in this case, we add in a trend and we use that to forecast the model. So we have a level and a trend, and beta is the smoothing parameter. So we're going to talk about the ETS framework, and in here we have an additive error models. So in this case, the error is additive, and we can have a trend and a seasonal effect, and go ahead and pick these different models, the one which works best. And we also have multiplicative error models, and once again with a trend and a season. So if we look at what is ETF, it's the error trend seasonality, and it's a framework for exponential smoothing models. And it can automatically select the best model from combinations of error, which is additive or multiplicative, and trend, which is none or additive drift, and seasonal, which is none or additive or multiplicative. And the models are defined in ETS as ETS E, T, S. So what is exponential smoothing? It's a family of forecasting methods that weight recent observations more heavily than observations in more distant past. And the types are simple exponential smoothing, or SES, and Holt's linear trend method, and the Holtz-Winters seasonal smoothing. So the formula for SES is that our next value or predicted value of y will equal some constant alpha times our previous value that we observed plus 1 minus alpha and the predicted value from the last time step. So if we look at the ETS model components, right, each ETS model has an additive or multiplicative, and we have none, and for the trend we have none, additive, or damped, and for seasonality we have none, additive, or multiplicative. So for example, if we said ETS A, AD, M, this is additive error, damped trend, and multiplicative seasonality. So how it works in R is that we could, for instance, use a library called forecast, and we can fit the ETS model to say air passengers, and then do a summary fit and an auto fit. So it automatically selects the best model based on the AIC, and it produces forecast with predicted intervals. So ETS is in the Fable package, and tidy forecasting, it's ETS with Fable plus T-Sybil. And if we look at the code example, we have the library Fable and the library T-Sybil, and we can define a array with air passengers and go ahead and index it, and then we'll fit it with a model using ETS, and then report the fit. So the ETS framework, it systemizes all the exponential smoothing methods, so SES and Holt Winters, and it provides a likelihood-based method for model estimation. And it selects the best ETS model using information criteria such as AIC corrected and BIC. And examples are the simple exponential smoothing and the Holt's linear trend and the Holt's Winters additive and the Holt's Winters multiplicative. So for example, we can forecast and a fit with H equals 12 and then auto plot. And H is the number of time steps ahead. And the forecast includes uncertainty bounds, and it's great for short to midterm forecasts. So when to use ETS, right? It's best for seasonal and trending data, and it automatically handles smoothing parameters, and it handles additive and multiplicative patterns. And its limitations is it doesn't support any external regressors, and probably use ARIMA for that. So in chapter 9, we're going to talk about the ARIMA model, but what we're going to see is that if we look at ETS versus ARIMA, ETS, it's smoothing based, and ARIMA is differencing based. Seasonality is explicit and must be specified using SARIMA, and it handles trends, both of them do. And if we look for a variable that affects the outcome but is not affected by it, ETS does not do it where ARIMA does. And for the interpretation, ARIMA is component based and it's easy, and ETS is component based and ARIMA is coefficient based. So let's look at an example. Don't forget this is a review from chapter 8, so we're using exponential smoothing. So here we see something that clearly has a seasonality and a trend. And so we can go ahead and load the library forecast, and I'm going to go ahead and load the library ggplot, and we'll have, sorry, there should be a return here, I apologize. So if we read in the file, so we wrote in the sample data ETS smoothing model data, some sample data, and we check the structure, and then we can go ahead and convert the second column. So I had the date in a format that wasn't suitable, so I went ahead and converted it. And we go ahead and fit the ETS model, right? And it's going to automatically select the best parameters. So we'll have model, ETS, and this time series data, and then print the summary, and then plot the data. So after ETS is called, it produced a additive and an additive damped trend and no seasonality, and it went ahead and used some smoothing parameters that are listed here. And alpha was about 0.27, and beta was about 0.17, and phi was about 0.88, and looked at the initial states, and we can see the AIC and the AIC corrected and the BIC, and show all these values. And it went ahead and fitted the model to the data. Or you can pick your own, right? So in this case, we'll go ahead and read in the values, and Once again, we went ahead and converted the time. And in this case, we're going to tell the model, the ETS model, that we want the error to be additive and the trend to be additive and the season to be additive. And go ahead and plot it and report it. So in this case, we'll go ahead and it found alpha to be about 0.32 and beta to be about 0.15 and gamma to be about 0.0001, right, which is a really small number, and went ahead and plotted it, and we can see how well our model did. So now we want to begin to talk about ARIMA models. And ARIMA models provide another approach to time series forecasting. So exponential smoothing and ARIMA models are probably the two most widely used models in time forecasting. And they provide a complementary approach to the problem, right? So exponential smoothing models are based on the description of the trend and seasonality, and ARIMA models are describe the autocorrelation of the data. So ARIMA stands for Autoregressive Integrated Moving Average, and it's used for modeling non-seasonal, autocorrelated, stationary or different stationary data. So why use ARIMA models? Because it captures this autocorrelation and it handles trends through differencing, and it's suitable for many real-world time series. So we mentioned stationarity and differencing. And stationarity of a time series is one whose statistical properties do not depend on the time in which the series is observed. So time series with trends or with seasonality are not stationary, and white noise series are stationary. So stationary terms, time series, have a constant mean and a constant variance and a constant autovariance over time. So it depends only on the lag. And stationarity is essential for many forecasting models such as ARIMA. So there's two types. There's strict stationality. That means that the statistical properties are unchanged at all times, at all shifts in the data. And weak stationary means there's a constant mean and variance and autocovariance. So how do you identify if it's stationary? Well, first, a lot of times the easiest way is just to plot the data and see if there's a trend or some change in variance. We can also use autocorrelation function. So if it's stationary, the ACF will drop off quickly, and if it's non-stationary, the ACF decreases slowly or remains high the whole time. There's also a statistical test like the augmented Dickey-Fuller ADF test, and we can find those in R. So here shows some data series, and we want to see which ones are stationary and which ones are not stationary. So give you a couple minutes, right, or a couple seconds to look at them and see which ones you think are stationary and which ones you think are not stationary. And there's probably two that are stationary. So if we look at the ones that have seasonality, right? We have some seasonality in D, and we have some seasonality in H, and we have some seasonality, although it's a little harder to see, in I. If we look for trends, then A, there's clearly a trend here, and C, it's not as clear, but there seems to be a trend here. And E, there's a negative trend, right? So it's decreasing as we go on in time. And F, there's a really slight decrease. And E, there's clearly a trend here as it moves up this way. And if we look at I also, we have an increasing variance here, as even if we take away the trend, it will be there. So this leaves only B, which almost looks like noise with some really strong peaks, and G. And G, you might be tricked, but if you notice over the long term, this seasonality, it's unpredictable. And so it's not a constant period for the change in this seasonality. So these two are the two stationary series. So don't forget, stationarity is a series that has a constant mean, variance, and autocovariance. And stationary is essential for many of the models. And non-stationary series have trends, changing variance, or seasonal patterns. And we said the best way to do it is to plot the data series, look for signs of trends or changing variance or seasonality. Sometimes we call changing variance volatility. And also look at the ACF plots. And non-stationary series decay slowly or don't decay at all. So we can use differencing. So differencing will remove the trend. So we take two data points and subtract them to make the difference. And you can apply this once or multiple times until the stationarity is achieved. So in R, we could just do diff series and then check with ACF and time plots after the differencing. We also have the log or the Box-Cox transformation. So this also stabilizes changing variance and looks for a log transformation or a Box-Cox transformation, which has more flexibility. So the seasonality differencing, if the series shows some seasonality, you can use seasonal differencing. So this is take the difference between a data point and a data point of one season ago, right? And it can be combined with regular differencing. So we could use the differencing series and the lag is equal to M in this case. Then we can verify stationarity. So after the transformation, you can check again. So we can make another time plot and see if make sure there's no visible trend or seasonality, and look for the ACF to rapidly drop off, and use statistical tests just like we talked about before, the ADF or the KPSS. And if needed, adjust the transformation strategy. And the goal is to prepare for modeling with stationary data. So for example, here is a trend, a data series with the trend, and we took the difference of the two data points, and if we look, the trend has been removed, and we're left with the time signal. So if we compute the differences between consecutive observations, it's one way to make non-stationary time series stationary. We can also use it for seasonality. So we can compute the difference between consecutive observations, or we can take the difference between observations one period apart. So if we look at stationarity in ACF, right? The stationarity is the time series. The stationarity of the statistical properties of the mean, variance, and autocorrelation are constant over time, and we need it for the ARIMA model. And if we look at the autocorrelation function, we measure the correlation between observations at different lags, and in stationary series, the autocorrelation drops off very quickly, right? So, and what we're saying is that the time series doesn't depend on what was going on in the past very much, right? And non-stationary series, the autocorrelation decays slowly, or it persists at high values. So if we look at the autocorrelation, if it's stationary, the time series is stationary as its statistical properties remain constant over time. And if we look at the autocorrelation function, it's going to measure the correlation between the observations at different lags. And for a stationary series, the ACF drops off rapidly to 0, and for non-stationary, it remains high. So here we see ACF of a stationary series, and here we see the ACF of a non-stationary series. So applying ACF to assess the stationarities, what we're going to do is plot the series to check for trend or seasonality, compute the ACF using tools. So in Python, you can actually use stats models and analyze the ACF plot. And if it rapidly decays, it's stationary. And if it persists for high value, it's non-stationary. And apply the differencing if needed, and then confirm again and use ACF for exploratory analysis, not as a standalone test. So here's some test data, right? So here I don't see any trend, or it's not easy to see the seasonality. It's actually just a time series of random temperatures, right? And you can see it drops off very quickly. So if we difference it, we see that we can go ahead and difference it at these at different lags and see what happens. So here shows some test data in the ACF of the original data, and we can see that it doesn't change, or it doesn't drop off quickly with time. And if we take a first differencing and also difference at logs 12 and 24, then we can see that it becomes stationary. So here's some real temperature data that was taken with a weather station at the sustainability farm at Stockton University, and this shows a couple of couple of months of data, or actually 2 years of data. So what we should see is a seasonal 12-month season, and also a daily cycle. And if we look at the original temperature, we end up with an ACF function that looks like this. If we go ahead and take the first differencing, we can see that it drops off, and we can also look at taking a seasonal differencing at 12 and 24, and we can see that we end up with an ACF that drops off reasonably quickly. So there's something called backshift notation, and it's a compact mathematical way to express the lag values in time series. And it's commonly used in time series models like ARIMA and exponential smoothing, and it helps to formalize the operations like differencing and lagging. So let y of t be the value at time t, and then the backward shift operator b is defined as b y of t is equal to y of t minus 1. So it doesn't look like at first that it's going to make that much of a difference or be that cleaner. But if we look at it a little bit deeper, what we can see is that if we have a single lag, so we have y of t is equal to, b y of t is equal to y t minus 1. So it's one time step back. And if we look at multiple lags and we have y minus k, we can write it as b of k y of t. So it becomes a little bit cleaner. If we look at the differencing operator, It's this upside down triangle times y is equal to y of t minus 1, right? And we get 1 minus b y of t. And in the seasonal, sorry, this triangle is upside down. The seasonal differencing should be y of t minus m. And we can write this as 1 minus b to the m y of t. So for example, in ARIMA models, what we're going to have is y of t is equal to phi of y of t minus 1 plus some error term or some uncertainty. So in this case, or residual. In this case, we can write it as 1 minus phi 1 b y of t is equal to our residual. If we look at moving average one, what we have is that y of t is equal to some residual plus theta e to the t minus 1. So and that can be written as 1 plus theta 1 beta or b times the residual. So in ARIMA models, we have phi of b, 1 minus b raised to the d of y of t. This just becomes theta b et. So it enables a compact form for estimating and forecasting. So the advantage of the backwards notation is that it's concise expression of complex lag features, and it facilitates model manipulation and solutions, right? So for example, with differencing and inversion. And it's widely used in software implementation, and it's crucial for understanding the algebra of ARIMA and seasonal models. So from your book, right, if we look at the backwards shift operator, it's if we look at b of y of t, it's equal to the previous value for y. So for some reference lag, instead of b for backshift, in other words, b operating on k has the effect of shifting the data back one period. So two applications shifts it back 2 periods. So if we have b y of t, what we're really saying is that b squared y of t is equal to the value 2 time steps ago. And for monthly data, we can use b12 y of t, in which case y, it's equal to the value for y 12 months ago. So the backward shift operator is convenient for describing the process of differencing. So for instance, if we look for the difference in y of t, it's equal to y of t minus the previous value for y. And in this case, can be written as y of t minus b y of t, or 1 minus b y of t. So the first differencing can be represented as 1 minus b. Similarly, the second difference can be computed. So for the second difference, we get y double prime is equal to y of t minus 2 y of the previous y plus y 2 time steps back. So this is written as 1 minus 2b plus b squared, which, if you remember your algebra, is just 1 minus b squared. So it's just an easier way to write these things. So if we look for the first differencing by 1 minus b, similarly the second differencing becomes this. So in general, the dth order difference can be written as 1 minus b raised to the d y of t. So for example, if we had a seasonal difference followed by a first difference, so we get 1 minus b raised to the m, then if we go ahead and multiply this through, we get 1 minus b to the m minus b plus b to the m plus 1 y of t. So what's this come out to be? It becomes out to be y of t, and then y of t minus 1, and then y of t minus m, and then y of t minus m minus 1. So let's talk a minute about the random walk model. So what is a random walk? It's a time series model which each value depends on the previous value plus some random value. So we have y of t is equal to the previous value plus some white noise. Random walk with a drift has the equation that y of t is equal to some constant plus the previous value plus some random number. And c represents the average change per time step. So the characteristics of a random walk is that it's non-stationary. So the mean and variance are clearly changing over time, and a strong dependence on past values, and there's no predictable patterns or seasons or seasonality. So how can you identify a random walk? Well, the ACF decays very slowly, and the differencing is required to achieve stationarity, and it's common in financial and economic data. So if you want to forecast with a random walk, its best forecast is the last observed value, and the forecast equation is equal to y of t plus h is equal to y of t, and the forecast interval is going to increase with the horizon. So with a drift, what we'll have is that the forecast equation y of t plus h is equal to y of t plus h times that constant c. And the interval increases more rapidly due to the drift. So this is good for things like stock prices, exchange rates, interest rates, and it's useful when shocks are unpredictable. The limitation of the value of the model is that it assumes no mean reversion, and it implies an infinite variance over time. So it's not suitable for series with seasonalities or trend without modifying it. So the random walk is simple but powerful model, and its key features is that it's not stationary, and it often is used in benchmark models, and the differencing can convert it to a stationary form. So to close out the first lecture, or the first part of Chapter 9, let's talk about autoregressive models. So autoregressive models, or AR, are models that use past value to predict future values. So the notation ARP, where P is the number of lags, and the equation is y of t equals c plus some constant times the previous value plus some constant times the value 2 times ago, and so on and so forth, plus the residual. So the key assumption is that there's linearity in the parameters, and that there's stationarity of the time series, and that the residual E of t are white noise. So if we were to subtract off everything, the trend and the seasonality and things, we'd be left with white noise. So the mean is 0. There's a constant variance, and they're uncorrelated. So once again, for stationarity, we have constant mean, variance, and autocorrelation in time. And non-stationary series require differencing or transformation and use ACF plots to check for stationarity. And when choosing the lag order or the order P, we'll use ACF and PACF plots, and we'll look for a sharp cutoff after lag P. And we'll use AIC or BIC for the model selection. So our equation is now for AR1, we have a lag of 1, and we're going to see that y of t is equal to a constant plus some value times y, times the previous value for y, plus the residual. So if we look for the interpretation of phi1, if phi1 is less than 1, it's stationary, and if phi1 is about 1, it's non-stationary and answer and equal to a random walk. So in estimating these IR models, we can use the least squares or the maximum likelihood estimation, and we'll use R functions, our ARIMA and AR. So forecasting with the AR models, the forecasts depend on previous observed values, and the confidence interval, of course, widens as you go further into time, right? It widens with the horizon. And the forecast equation uses future values of the future value recursively. So if we look for, here's two examples. The first example is we have 18 as the constant minus 0.8 for phi1 and plus some residual. And for AR2, we have y2 equals 8 is the constant plus 1.3 is phi1 and negative 0.7 is phi2, right? In both cases, the residual is the normal distribution of white noise with a mean of 0 and a variance of 1. For the AR model, if phi1 equals 0 and c equals 0, then y of t is, of course, just white noise. And if phi1 equals 1 and c equals 0, it's equivalent to a random walk. And if phi1 equals 1 and c does not equal 0, then it's equivalent to a random walk with drift. And if phi1 is less than 0, then it tends to oscillate around the mean. So if you think about it, if the previous value was negative and we multiply it by a negative number, it becomes positive. And if the previous value was positive and we multiply it by a negative number, it becomes negative. So if we look for the strengths and limitations, the strengths are as simple and interpretive and interpretable, and it's good for short-term forecasting of stationary data. And it doesn't do well with trends or seasonality, and it's sensitive to non-stationarity. So in summary, the AR models forecast using past events. The stationarity is crucial, and the lag order selected via PACF or AIC or BIC, and it's a foundation for the ARIMA and the ARMA models. All right, so that ends that first half of Chapter 9, and I'll be back with the second half soon.